thermal instabilities in the ISM between the warm and cold neutral phases, gravitational instabilities and turbulence that all lead to the production of these filaments. And then when this is photoionized, you will get pressure gradients that cause the expansion of the H2 region on large scales because of the fact that these are just finite size filaments. But you can also see structure on many other scales. And this causes there to be flows, not just the ordered velocity like the champagne flows, but you get smaller scale flows from globules. And these flows can be mildly supersonic inside the H2 region. And when they collide with each other, they can form more density structure and they can form temperature fluctuations as well. And we also have a secondary roles for the effects of stellar winds from the ionizing star, jets from low mass stars, and in some cases radiation pressure. So in summary, the common thread from all these ideas, from the most simple to the most complicated ideas, is that it's the thermal pressure of the H2 region that drives the dynamics, and that is what produces the structure that we see in these regions. And obviously, this thermal pressure comes via the radiation from the hot stars, heating and ionization, increasing the pressure. And so the H2 regions are mainly governed by the thermal pressure gradients and the pre-existing density structure, with these other physical processes being important to a lesser degree, but something that also needs to be considered in many cases. Okay, so to take an example of a more evolved and more luminous H2 region than the one I showed before, consider the Lagoon Nebula. So this here again, if we look at long wavelengths in the submillimeter emission here of cold dust, we also see sort of filaments with dense cores lying along the filaments. The same structure can be seen in extinction against the galactic the field stars in the galaxy behind the H2 region. And this is a near-infrared image. So this you can't see, it doesn't show that clearly the ionized gas. You can see a bit of the ionized gas here as continuum and line emission that comes in these infrared filters. To see the structure a bit more clearly, we can go to the mid-infrared. In this case, what's shown in green here is the emission from neutral gas, I think mainly from PAHs in the neutral photodissociation region around the H2 region, whereas the red and orange comes from hotter material, hot dust that's inside the H2 region, possibly some line emission as well. Of course, the emission from the ionized gas, maybe we can study in most detail in the optical emission. And this is a composite of different optical emission line filters. It's traditional in these sort of images, at least in the optical, to use a color scheme in which the most highly ionized, the lines that come from the most highly ionized species are shown in blue, and then the sort of intermediate ionization in green and the lower ionization in red. So you generally see in the emission from the ionized gas, I mean, I think this is oxygen 3 H alpha and nitrogen 2 in this particular case. You see a general transition from more highly ionized material in the center to less highly ionized material in the exterior. And I'm going to explain a little bit of that when we talk about ionization parameters later. But this is all ionized. This is, even when I say highly ionized and less highly ionized, the hydrogen is all more or less fully ionized. The main thing that's changing here is the ionization of the heavy elements. But despite the general trend from more highly ionized in the middle to less highly ionized on the outside, you can see that there are many exceptions. You do see less like the red emission from regions that are close to the center of the nebula, and this is due to the complicated filamentary molecular structure in the medium that this nebula is evolving in, which leads to there still being molecular gas that's quite close to the ionizing stars. I'm just going to zoom in on a region here. If you remember that there were various molecular filaments, some of them most of them on the outside of the nebula. Some of the molecular filaments are kind of coming in a sort of spiral fashion towards the middle of the nebula, and this is this region here. And when you get this sort of clumpy filament that's directly exposed to the ionizing radiation, you often get these globule type, bright rimmed globule structures in the ionized gas. And these I would like to posit are quite important for generating the velocity fields that we see inside the H2 region. And one interesting thing here is that although the global ionization front is concave and it's closed, and where you have a globule flow, where you have these globules, bright rim globules, the ionization front is convex, and that makes a big difference to the dynamics, and means that you can have a transonic flow of ionized gas that comes off these convex globules. Okay. When you zoom in even further, you start to see the texture of the ionization front, and here, so you do see structure almost down to the limit of what we can resolve with even the HST or something. But although there is interesting structure down at these small scales, the amplitude of the fluctuations of brightness at these small scales is in fact quite small. So in fact, if you're considering what's the important scale for the fluctuations in brightness and in other density and other quantities in the nebula, the fluctuations at small scales tend to be not so important as the fluctuations on larger scales. So here we're talking about scales of about a fraction of a parsec. Okay, so this is just a preview of what I'm going to show about the simulations, but this sort of state of the art from maybe a few years ago of what we could simulate on with numerical radiation hydrodynamic calculations of the evolution of H2 regions is now doing a quite good job of reproducing the sort of structure in the emission of different optical emission lines that you see in real nebula. Here on the left we have the Lagoon Nebula. This actually has been processed, so this is certainly reality in scare quotes, because this amateur astronomer went to the trouble of removing all the stars from this image, which was a very impressive feat, and it was great because we can compare it with our observations without having to put the stars in our in our simulations. Right. So, what sort of ingredients need to go into models of H2 regions? Well, we're going to start with the ionization. The single most important parameter for an H2 region, I would say, is the ionization parameter, and this has two different flavors. It has a global version and it has a sort of local version. So here we're going to concentrate on the global ionization parameter, which is defined for the entire region. So this is given by, it's basically the ratio of the density of ionizing photons to the density of ionized gas. And it's given by this form. And in particular, if you assume photoionization equilibrium and ionization bounded region, you can show that it's proportional to the product of the density, ionized density, and the ionizing luminosity to the power of a third. So more luminous regions and denser regions tend to have higher ionization parameters. And this shows a large variation in different types of H2 regions. It can be very low in cases such as Planetary Nebula that are that have evolved because they're low density and low ionization. Also, sort of large H2 regions around runaway OB stars, such as Zeta Fuci, also very low ionization parameter. Then there's a sort of intermediate range, which covers the sort of typical H2, small H2 regions, such as those that are seen all over the galaxy with Spitzer, larger H2 regions like Orion, and giant ones like Carina. They all have ionization parameters of order 1%. And then if you go to the biggest, most massive star clusters in our galaxy, you can get ionization parameters that are approaching unity. I won't really be considering that. We'll be focusing on these values. And the reason for that is that the physics is actually quite a lot simpler if you're around U of 1%. Because if you go to low ionization parameters, then photoionization equilibrium tends to break down. Whereas advection terms are important in many of the rate equations. Shock heating is more important. The ionization front is very floppy. High ionization parameter, dust starts to dominate, so you need to be very careful about how you consider dust. Dust dilution will be much more important than high ionization parameter if the dust to gas ratio is the same, but of course you don't really know that. Radiation pressure and winds are also important and tend to evacuate a central cavity in these regions. Okay. So the other flavor I mentioned of the ionization parameter is the local ionization parameter. So you can define, so the global ionization parameter is sort of a typical value of this ratio of photon to gas densities over the whole region, but you can also define the flux divided by the density locally within the region. And if you assume that the hydrogen photoionization is in equilibrium with radiative recombination, then you can show that the fraction of ionized hydrogen divided by 1 minus x, which is the fraction of neutral hydrogen, is proportional to this local ionization parameter. And this, if the density were constant, then the flux is what determines the local ionization parameter, and that should decline monotonically with radius by geometrical dilution and by absorption due to the trace fraction of neutral material in the H2 region. But wherever you have the density increased for any reason, for instance in a shock, cooling zone behind the shock, then that will also have an effect on the ionization parameter and will tend to decrease it. Okay, and we're going to say that this x over 1 minus x is a measure of the ionization fraction, where if x over 1 minus x is very large, the hydrogen is almost fully ionized, and if it's very small, then it's almost neutral. Heavy elements in general is more complicated, but if you assume a certain ionizing spectrum, then generally the ionization of any other element for a certain shape of ionizing spectrum is that at least the 0th order is a function only of the ionization parameter as well, so is also a fraction of the degree of ionization of hydrogen. So this is the explanation for those multicolor RGB colors of H2 regions, where if you look at the line of oxygen 3, for instance, that comes from O++, then this is the abundance of oxygen plus here we multiply by the electron fraction to give something more or less proportional to the emissivity. Then it requires ionization of order 10 to the 3 in this, which means that it's more than 99.9% ionized. Whereas the nitrogen 2 line peaks here around 10 to the 1 and 10 to the 2, so that's peaking in between sort of 99% and 90% ionized. Whoops, okay. So, as I mentioned before, when you have a convex ionization front, such as in a globule, then you expect to have a photoevaporation flow from the head of this ionization flow. This is a nice example from Carina, in which you can see the bright rim here, which at least theoretically, have a density that has a certain law that we can work out. And then here, it seems to be that you have some sort of shock, and then you have the sort of the interior of the H2 region. So this is consistent with what we expect, that these photoevaporation flows sort of carve out a cavity in the H2 region. In this case, because the radius of curvature of this globule is very, very small compared to the radius of the H2 region, the global radius of the H2 region, then the cavity that's carved out is quite small. But this same process occurs on all scales, and if you have a globule which is radius of curvature is more than about 5 or 10% of the radius of the H2 region, then you can basically carve out, you can dominate the entire dynamics with these photoevaporated flows. So I'm just going to briefly mention a little some of the work we've done on simulating these flows. There's various complications you can put in. This case, the complication we went for was magnetic fields. Magnetic fields, if they're strong enough, then the main effect is to cause the collapse of the globule, which is, well, the globules are always are imploded by the pressure of the ionized gas, the same pressure that causes the ionized gas to flow outwards. The back reaction from that implodes the globule. And if you have a strong enough magnetic field, then that implosion is not cylindrically symmetric, but is just along the magnetic field lines. And that's the case for these simulations that I'm showing here. These are just synthetic observations in optical emission lines of these observations. So there's the initial stage of the implosion seen from different angles. So when we look sort of from the top, we're pushing things across the field lines, so we can't really implode the globule very much. But when we're looking from the side, when the magnetic field lines are going this way, then the gas can be easily crushed down onto the axis. I think it turns out that the magnetic field that we're putting in these globules is probably too large to be realistic. And in fact, in real H2 regions, you see something that's not quite as asymmetric in that. This is just other simulations varying the angle of the magnetic field. So that's the globules are an important ingredient in the dynamics of the H2 regions. But obviously, to simulate an H2 region in its totality, you need to have some more complicated density distribution than just a simple globule. So that's the work that I mentioned earlier, that we use simulations of the gravitationally unstable turbulence in neutral molecular clouds as our initial conditions. We take a collapsed core in those simulations, and we say that we form a star there, and then we let the high mass star, we let the H2 region evolve. And so initially, the H2 region is expanding in a dense environment, but eventually it gets to the edge of it, and then it's sort of, you get something like in the Tenorio-Tagle idea that you have a breakout of the ionization front in certain directions. The initial breakout doesn't involve any flow of gas. In this case here, the warm gas is still all confined in the middle, but we've started to get regions that are optically thin and can allow the ionizing photons to get out into the lower density neutral medium around the core in which the star forms. Eventually, the gas itself, the expansion of the ionized gas, will also get to the field density gradient and will start to expand rapidly. And in that stage, the neutral shell tends to break up into lots of small globules. So in this simulation, actually, although there was structure in the molecular cloud before we started the H2 region, a lot of the structure that we're forming here, especially at small scales, is due to instabilities in the expansion. It's probable that our initial conditions actually didn't have enough structure in them. If you compare, we should maybe use some more updated simulations for doing this. But it's interesting that the instabilities can actually generate this sort of structure, even if it wasn't there to start with. So I'm just going to quickly show movies. So the great thing about simulations is we're not limited to one point of view, but we can look at the H2 region from lots of different angles, and depending on the relative orientation, then certain regions might be seen in absorption, or if I spin it round, we start to get seen in emission. So these simulations are all well and good, but they're lacking lots of things. Okay, so this is just the neutral gas, we'll jump that. They're lacking the stellar winds, for instance. And in those cases, lacking magnetic fields. So the implications for the kinematics of the H2 regions are that you can maintain roughly sonic velocities for the entire evolution of the H2 region, as opposed to the boring Koch-Spitzer evolution in which the velocities start off small and fall down. That initially, when in the Champagne flow phase, the expansions are mainly radial. Towards the later phase, the flows, inward flow, pointing flows from globules tend to start to dominate. So the mean radial velocity falls off, but the RMS velocity maintains a value of about 10 kilometers a second. Okay, I'm going to have to speed up. So observationally, you can also look at the kinematics, and you tend to see a rather disordered velocity field. This is some isovelocity images of emission lines in Orion. At high velocities, you see the flows, Herbig-Haro flows. Although these look very impressive, they actually represent a very small fraction of the total emission and the total mass. So the majority of the energy density of the gas is in lower velocity, roughly sonic motions, and you see quite large scale density gradients in the gas. The blue and the red indicate different velocities, but you also see much smaller scale variations. One way of studying this is statistically. I haven't got time to explain this, but if you take isovelocity images and you compare the structure you see in them to an image that's integrated in all velocities, then you should see more structure in the thin velocity slices, because as well as the emissivity variations, you're also seeing velocity variations there. If we apply that to the Orion Nebula, as in a paper that's in press at the moment, Jane Arthur in the first author, you can find that if you look at the power spectrum of the thin velocity slices and compare them with the thick velocity slices, you can have a diagnostic of what the statistics of the velocity fluctuations is. It turns out to be, as always in these things, to be consistent with Kolmogorov power law, which is quite nice. Shocks and winds. Shocks driven from the stellar wind of the ionizing star can be very important in the more massive regions in which you have evolved stars like Wolf-Rayet stars, which have more powerful winds, and also that tend to have higher ionization parameters anyway. In the more typical H2 region, even when you can clearly see the effect of the stellar winds, such as in the bubble nebula, you see it's confined to a small fraction of the total radius of the H2 region. So most of the H2 region is probably not affected by this wind. Not to any great extent, although of course it could be that it's a leaky shell. That's another question. Other effects of winds or flow is shocks. You can use as a diagnostic of the direction of the local flows of gas. This is the case at LL Ori in the Orion Nebula, where you have this beautiful stationary bell shock here, which is formed by the interaction of a flow from the T Tauri star here, possibly evaporated disk, and the Champagne flow of ionized gas in the nebula. And you can either have an interaction with the Champagne flow, or you can have interaction with the stellar wind. You get the two-shock flow pattern. Depending on the densities of the gas, you can have either the outer or the inner shell being the one that emits radiation, or both. In Orion, we see many of these bow shocks, and we can map out their positions and their directions, and by looking at how close to radial they are, we can sort of compare the systematic radial expansion with the turbulent flows in the nebula. I'm going to jump. Yeah, there's some very strange things you see when you map out the positions. You can see a spiral pattern in the bell shocks, which is the shadow of a similar spiral pattern in the brightest ionization fronts. Cloudy. How does that fit in my remaining 1 minute? Okay, so there's been two main teams, as we say, that two main approaches to studying the ISM in general and H2 regions in particular. Those that can concentrate on the dynamics. This is like an isothermal calculation of turbulent dynamics, so there's almost no physics in there, or no some microphysics, but there's plenty of complicated dynamics. And the people who like to concentrate on the microphysics, here is another Gottfried diagram, this time for oxygen 2. Now really we need both of these approaches, because if you consider the conservation equations for any species I, then you have the sort of dynamic terms, the evolution plus the divergence of the flux of it. Then you have the sources and the sinks, which is the microphysics, the radiative rates, the collisional rates, the ionization, etc. So how can Cloudy help with this? There's two ways. One can expand the microphysics codes to include dynamics. And that's something that Gary and Robin Williams and myself, to some extent, have been involved in. And this is an example of an application recently made of this, which is calculating shock models for Wolf-Rayet Nebula using Cloudy, in which this is the sort of collisional ionization equilibrium cooling curve. And then these are the cooling rates as a function of time in these shock models. So you initially have an out of ionization under ionization, so enhanced cooling very fast, and then you have an out of equilibrium cooling where it's over ionized. And then the other way that Cloudy can be employed to help things is to act as a sort of subgrid model for the hydrodynamic codes. That is, hydrodynamic codes with any finite computational resources are limited in their resolution, and often there's physical processes occurring on much smaller scales than we can explicitly model in the hydro codes, and Cloudy can be useful there. This is just an example of calculating the turbulent energy dissipation in weak shocks in the H2 region, which is in green, compared with the ionized emission in purple. And using Cloudy, using this turbulent energy generation, we can use full atomic physics models to calculate the effects of this on the temperature fluctuations. Okay, that all have to do.
Very much, Will, for a very nice presentation regarding physics of H2 regions. I'm glad you brought in Cloudy, of course, and also I'm glad you did not forget the magnetic field. Thank you very much. Okay, questions, Professor Ferland.
So I didn't quite pick up what you said about the turbulence. So Orion has a level of turbulence that runs across the nebula, and I think it's still true that this turbulence seems to scale with luminosity, increasing as luminosity of the H2 region. So the question is...
the luminosity of the H2 region in Orion?
No, in samples. This is one of the Terdovich original luminosity indicators.
Okay.
So what is the nature of the turbulence? Does it affect the pressure in the H2 gas? What's going on with the observed turbulence?
Well, of course, when you say turbulence, you're saying you mean line widths. Okay? And I haven't really got much of an idea about what happens in the larger H2 regions. I know that, yes, it's been well known for a long time that there is this luminosity sigma relationship in giant H2 regions. And I think there is still question as to what's going on there. I think I think the line widths that you see in giant H2 regions are much larger than the line widths that I'm talking about here that are generated by the thermal pressure gradients. So I think that you have to have some help from the stellar winds or from the gravitational potential. I mean, I haven't talked much about gravity because in regions like Orion, the gravity is not very important. You can calculate a sort of a gravitational sort of scale height, taking the sound speed squared divided by the gravitational acceleration. And in the case of most H2 regions, that's very large compared to the size of the H2 region, so gravity shouldn't be important. If you go to giant H2 regions, then that's not the case. The gravitational scale height is comparable to or smaller than the size of the region. And so, the gravitational effects on the dynamics should be important, as well as having, once you have an older region of getting to more than a few million years old, you start having the Wolf-Rayet stars, which have much more powerful winds that can also influence the dynamics.
The magnetic field will also automatically scale.
To some extent, yes, but although in the neutral and molecular gas, the magnetic pressure is larger than the thermal pressure. Typically, you have supersonic turbulence, and you have roughly equipartition on average between the ram pressure of the turbulent motions and the magnetic fields. In the H2 regions, the turbulence is subsonic. There are bits that are supersonic, but if you take the RMS velocities, they generally work out to be subsonic. And the magnetic pressure is generally at least 10 times smaller than the thermal pressures. So although you could have some amplification of the magnetic fields from turbulence, I think the turbulence is not as strong as it is in the molecular clouds, and the magnetic field to start with is weak. So I don't think it would be a major effect.
These are smaller than the observed values in Orion.
What are? Turbulent what? No. Well, it depends. No, this is Orion. No, in Orion you see something that's consistent with this. Yeah.
I think we'll have to move on to the next talk. We're running just slightly behind time. I'm sorry about that. Is it a quick question that you have?
I'm not sure. I just wanted to ask what is causing this complexity of the medium before even the ionization.
Okay, yeah, I mentioned that briefly, but I did it fast, so it's not really the topic of this talk, but what people understand is that it's a combination of gravitational collapse that's maybe induced by colliding streams that in the warm neutral medium that become thermally unstable, pass to the cold neutral medium, then breaks up and is gravitationally unstable, and then collisions of sheets will tend to form filaments, and sort of accretion along filaments and collisions of filaments will tend to form cores. It's all very complicated, and there's a lot of people who work on it. We don't understand all the details, but we can see, just looking at the Herschel images, you can see the reality of these filaments.
Okay, thank you very much. Let's thank Will again for a very nice presentation. Coming up next is Bob Odell, who will tell us about the Orion Nebula. There's probably no one in the world who has studied the Orion Nebula more intensively than Bob Odell. You're hearing it from the master. Some might even argue that the nebula should be renamed the Odell Nebula, but Bob would be way too modest to consider such a matter. One other brief announcement. I noticed in the schedule, after Bob's presentation, there is a poster session series. How many here wish to make short presentations regarding their posters? Looks like about 6 or so. So what I would request is that after Bob's presentation is over, if those who wish to do so would line up over here in any order, and then each will have the opportunity to give a brief presentation. Thank you.
I'm sorry for the delay.
Well, it's not uncommon that small technological glitches develop. We have a slightly flexible schedule, so we should be able to accommodate that. I've never before been in a lecture hall for science that also has a baby grand piano here. We could almost imagine having a pianist playing a crescendo to get everyone in the mood for the next talk. But I guess that's one small detail that the local organizing committee, which has done so well, just didn't happen to arrange. Next time, perhaps.
Well, no progress is being made.
Restart.
What?
I'm going to restart.
No? Should I help?
Okay.
Bob has asked that I not abuse him as the speaker, as chair, because he pointed out that tomorrow he will be the chair when I speak, so have to be very careful.
Yes, that's the real world in operation.
Right. Now we're looking at reality rather than simulation.
Although we do not have it worked out, I am optimistic that Will and Miriam will. So let me start, in order to keep things flowing, let me start without graphics. I will give a very different type of talk than the beautiful presentation you saw from Will Henney. And mine will be a historical approach to how observations lead modeling and how modeling lead observations in using the Orion Nebula as an example. And I thought I had.
Do you have a USB with the talk?
This, but it will not have the movies. I would have to integrate the movies into it.
We could try restarting it. For some reason, it doesn't seem to recognize the external display.
Yes. Who has the chip right?
Abraham Roldán, oye, ¿puedes cambiar el antes de que bajes el, ¿cómo se llama? Cañón? Gracias.
I think it's going to work.
Cámbialo a este. No, el cañón está bien, más bien el. Ajá, exacto. Ahí está. No, pero no ahí. El que sigue. El que sigue. HDMI.
No,
Sí, RGB. Sí. No. Ahí, déjalo.
I use this that would be fine. I think that's better. I thought going from Mac to Mac would work. But.
So you agree with that?
Fine. I'll talk right after the first. Okay. You tell me when.
Now? Because of slight technical difficulties, we're going to make a slight change in schedule. We're going to have the poster session grouped now starting momentarily. So, and then that will give Bob and others time to work out the technical matter. So those who are...
Abraham, ¿nos puedes poner HDMI, porfa?
Those who are wishing to make poster session presentation, ask you to come over here to this side of the hall. I know it's a little bit problematical. Perhaps you didn't plan to speak just at this moment, but a little bit later. However, Hallelujah.
Good morning. So this talk is how modeling and observations go together using a historical approach. Why not start at the beginning? This is a view of Orion from the constellation from a very dark location, and as seen by the people of the Maya in Central America, who could see, unlike people of today, the clouds of light around this star. And indeed, more changes will be made. Indeed, part of their foundation legend was that this was the smoke of the campfire of the people who created the Maya. Now, with the invention of the telescope, things changed. Now, Galileo Galilei made that first astronomical telescope and sold them on the basis of they could resolve fuzzy things into stars. Galileo never recorded the Orion Nebula. A few decades later, Christian Huygens did record this drawing of the object, and as you'll see in the various pictures that we show, that the point of orientation is the dark bay that's located over here. So you have observations, you create a model. That's what the Maya did. With time, people like William Herschel developed very powerful telescopes, created much better views, and for the public, much better drawings of what the Orion Nebula is like, until it became a very popular object early in the 19th century. And you see this quotation of lifted from Tennyson's Idylls of the King, this particular section. And you can read it faster than I can mouth the words. And notice that last phrase, of some vast charm concluded in that star to make fame nothing. And I appreciate that statement. Soon after, with the introduction of spectroscopy, which is, after all, worth 1,000 images, you see it was recognized there were two types of nebulae. Some were reflection type, some were with lines. And the person who resolved this is generally not appreciated by students of gas bags, was this guy, Edwin Hubble, famous for his extragalactic work. But part of his PhD thesis was showing the explanation between reflection nebulae and H2 regions, showing that the difference was the presence of a hot star in the latter. Yeah, and with time, Orion was imaged more and more. Although this is an HST image, it's presented at much lower resolution than the HST. So you could then identify the entire region here, about 1/2 degree in size, as the Orion Nebula. But the bright part in here, which is called the Huygens region for historical reasons, is where the story lies of what the object is really like the center of a cluster of some thousands of stars, including hot stars, but not as hot as some of those that Will just showed us. And the correct model that we accept today was posited by Bruce Ballack in 1974. The work overlapped with a much briefer study by Ben Zuckerman, published the year before, but Zuckerman acknowledged in his brief paper that Ballack was coming to the same conclusions, but with vastly greater data set. And so the conclusion was that Orion was a blister on the front of ionized blister on the front of a giant molecular cloud. With time, improved spectroscopy, that's proven to be the case, that you look at different tracers. As you look down on this flat nebula, we're looking on it basically flat on in most of the areas. And if that's the case, then you expect behind it, beyond ionized later, to be a PDR, which has its own characteristic markers and velocities and densities. Then the ionization front, which has its own particular velocity markers, densities, thickness, low ionization, the helium neutral zone, its own velocities, densities, and size. And this is important here because this projects the nitrogen emitting layer is only about 1 arc second in thickness. So the span of the nebula I'm showing there is a few hundreds of arc seconds. So it's a very thin layer. And then there is a higher ionization zone, which is traced best by oxygen 3. So you see this run of velocities where, and this should be improved because this is a smaller number here. This run of velocities tells you that you have a photoevaporating ionization front where material is flowing out towards the observer. Now, a very pivotal paper was published in 91 with Jack Baldwin, a very careful observer, Gary Ferland, by then already a master of a very versatile cloudy program, and they use cloudy to build up an accurate picture of Orion. They could, for the first time, take a model and reproduce the spectrum that is observed down in the middle of the nebula. A very big step, and everything since then is essentially built on this paper. So what we're looking at when we look at objects like this is an ionization front on the front of a giant molecular cloud. Now this image is color-coded by ultraviolet radiation, although it's made of visual photons, so that the highest energy potential is rendered oxygen 3, rendered in blue. Medium ionization potential is in H alpha, green, and nitrogen 2, the lowest ionization potential, is rendered in red. And in the Baldwin paper, Gary Ferland figured out something that had been stated before, but he used it and emphasized the basic physics behind it, namely that the surface brightness of a blister nebula should be proportional to the number of ionizing photons arriving at its ionization front. And from that, Zheng Wen, a graduate student of mine, was able to build a three-dimensional model of the Orion Nebula, and for the first time, so that the somewhat simplistic model of Bally, of its being flat on with some interesting ridges, was refined even farther. So observation and modeling were feeding back one to the other. But going back to the 1930s, it was known that some of the bright stars, or the brightest stars in the Orion Nebula cluster, had foreground absorption lines. And Adams showed this first. And by 1993, I guess, my students and I did a study where you looked at the various stars of the trapezium, plus that's a star off on the edge of the Huygens region. In this case, the helium 3889 line, and you can see it has multiple components, but a common component here. And these are heliocentric velocities, so if you're a radial person, shift by 18 kilometers a second. So this told you that there was a layer in front. Paul van der Werf and Miller-Goss, in Paul's thesis of '89, showed that there was a 21 centimeter absorption line there, and that concept has, that's 21 centimeter absorption line against a radial continuum, and that is a subject that Tom has built, a discovery Tom has built on for decades now, and we'll speak about tomorrow. And now that veil surrounds the whole region, but where you can see it is here, that in a study let me go back, with Jessica Harris, we mapped spectroscopically with bigger spacing the entire extended Orion Nebula. What we discovered there is that something that was shown in the Baldwin paper, namely there was a strong backscattering from the dust and the PDR, so you could see starlight in reflection, whereas what Jessica and I established built on something that Manuel and I had first presented evidence for some 40 years before. Namely, the region out here is simply scattered light, mostly, I should say, scattered light from the nebula itself. So it's horribly complex to interpret this spectrum out here, because you cannot divide the reflected light from the light originating in that area. The resulting model of this is shown here, where I take two cuts. I show two cuts, one here across this direction, the other here in this direction. And that model is depicted here. So this is from the northeast, that is the upper left in the diagram, to the down in this direction. And you see that the trapezium stars down here, the source of the ionization, a blister nebula that's very concave, going out to the size of about 1/2 degree. You look in the other direction, and you, again, are able to detail the structure of this concave region. Now, Tom and I have a friendly debate whether or not this Orion South cloud is here, a plurifratal, if it is a finger, actually a finger sticking out, or if it, as he argues, the result of an additional H2 region behind the main ionization front. The subject of the veil has been addressed many wavelengths. I cite here a recent paper, the last in a series by Nick A. Bell, and Tom treats the veil in a recent radio study. But what Nick has done is study it over an entire range of wavelengths. And here, for example, from the optical, the ultraviolet, so here are molecular lines in the veil. So this allows you to determine the physical conditions, and the 21 centimeter observations of the same line of sight. Now, the veil is very important to modelers because this is about the only example where you actually have the slab of gas, where you know where it is, you know the ionizing source, that is what determines its ionization, and you know the strength of the magnetic field that's in it. So this is probably the test piece, the best test piece for theories of combining radiation and magnetic fields. Enter this telescope, which allowed us to image the Orion region at unprecedented resolution, at least in the optical. And I should point out that there are two senior people from the Hubble and the room that, in addition to my role, that David Lambert was one of the senior team members in defining the spectroscopic capabilities of the HST. So this is a modern image of it. We've seen it many times before. This doesn't do justice because it projects to about 1/5 of the resolution of the images. Today, where we are, we're with a 20-year time base, we're able to look at changes within the nebula, which are almost exclusively the outflows that are originating from young stars. So this, for example, is an image that's a ratio of the old image divided by the new image, so that here it is in oxygen 3. So an object that's moving, say here to the left, the black is the leading side. And so you can now measure how fast they're going. You can measure them tangentially, determine the radial velocities, and get their spatial velocities. And you see that the flows seem to be left and right. You get a very different picture when you look at nitrogen 2. Remember, nitrogen 2, low ionization, a very thin layer. And here it looks quite different, where the flows out here off to the west are very different and have a different origin. This is summarized in a movie I show here. Watch in particular on the first pass through this squiggly feature here. This is down close to the edge of the Orion south regions. So watch the jet there. So it's moving out from behind the ionized layer here at about 150 kilometers per second. So we're actually seeing a jet that originates from a embedded star, optically invisible, that lies back here. I'll play it one more time. So watch things move as we go along. And you can also see objects here all moving out in the opposite direction. So that from time-lapse imaging, we can combine this with modeling of what the outflow is from young stars to really start to understand what's happening. And here against a standard color coding image of that same region, we can take these velocity vectors, for example, this jet here, and say, since it's moving this way, its source must lie back here. This is the feature we were just seeing in the movie. So the source is back here. The movie, which was made since this image, points right at it. And the other flows here, like another linear flow here, must lie from one of the sources off in these directions. It is most likely a so-called Mach 77 infrared source. Thank you. I push the standard button. I've been stepped on by the system. The other thing that we're doing right now, for example, and this is with Manuel and Will and Gary, is to look in detail across samples across the nebula. And an idea that Gary came up with is the small-scale variations in radial velocities were due to tilted features in the main ionization front. We see them here, and we can determine the physical conditions of temperature and density across these regions. So this is allowing us to build up a detailed model of the nebula. One of the bottom lines of it is something that Will referred to and illustrated nicely, that when you cannot explain this fine-scale structure without introducing the concept that the structure at the PDR is highly irregular rather than being the smooth model that we have in the past. And this is where we are, and as Will showed, in terms of combining models and observations. So this is the beautiful object, and it continues to enjoy popular attention. This is the cover of a recent Philip Glass composition titled Orion. So it's something everybody is interested in. I'm glad to take questions with Tom's permission. I had intended to play the fly-through movie during the discussion, but let's go ahead with whatever you want.
Let's get started with questions. Bob can take just a moment as the first question is coming out to get the movie
Well, I will shout.
Actually, you should keep this.
Deaf as a post.
Okay, thank you very much, Bob, for a beautiful presentation. I have to say those images, yes.
So this is taking the model and doing a simulated fly-through. You'll notice that we're exceeding the speed of light, and even without that, we're approaching it. There is no dilation. Okay, you saw part of it. That's all.
Those ratio images that you showed, Bob, were really stunning. It's just astonishing what the Hubble Space Telescope has been able to do with high resolution and a long time frame. Okay, questions?
The question is naive questions.
Others will want to hear it too, Sylvan.
Just a naive questions about the blister. It seems like in your picture that have been published, they've completely excavated. In other words, there's no filaments in them, high-density filaments like molecular gas or even dust. So I was just wondering, how much do we know about what the content of it is on smaller scale? Is there a molecular gas that is embedded in terms of small filaments or just dust?
Well,
or is it just fully ionized, essentially?
I think most of the features that were left behind, this is basically a champagne phase nebula. And all of the free-floating things have been completely photoionized. The exception is this Orion, I would argue, is this Orion South figure, which is massive enough to have survived that. The filaments that we see across the nebula, and this goes back to Bialik, the basic idea, is that these are regions that are seen almost edge on, bright bar in particular, and of course this is a subject of people who love PDRs and love to model them. Will and I have both shown that there are actually numerous smaller bars like that throughout the nebula. So those two are showing the original conditions. And if they are, then it means these linear features represent filaments that were in the molecular cloud before the ionization started.
Other questions? Okay, let's thank Bob one more time. We now move to the poster session presentations, and I understand there's a queue here of slides to be shown in connection with that. So I'll ask those interested in giving presentations on their posters to queue up here. Thank you very much.
Okay, for the poster presentation, we are waiting for, in this order, Avila Chatzisco, sorry if I don't pronounce well the name, Henney, Escalante, Espiritus, Flores, Galindo, Gomez, Guzman, Hernandez, Kaplan, Medina, Michel, Recci, Reyes, Robleto, Ruiz, Valerdi, yeah. Okay, so in this order, please.
Those of you getting close to presentations, if you have a minute, actually we can probably go a little bit closer to 2 minutes. After a minute, I'll raise my hand just to remind you that it's time to wrap up. Giving a 1-minute presentation is a real accomplishment. Good luck to all of you.
So first one.
Okay. Yeah. Sorry for this. Good morning, everyone. I am Alejandro Avila. I'm a master's degree student in this institute. Today, I present a new approach to derive oxygen abundance based on strong line indicators calibrated through a large catalog of H2 regions with estimations based on the so-called direct method. Our method uses all the possible line radios and provides with the best estimations of the oxygen abundance based on a probability distribution for a subset of pair of line radios. With the current approach, we provide with a calibration with an error of the order of 0.09 dex. So feel free to ask me any questions. We have the poster number 1. Thank you.
Hi, this is poster number 3. My name is Marios Hadzikos. This work focuses on the problem of cooling flows in elliptical galaxies. We work with a sample of 9 galaxies drawn from Ciro Pinto's TIERS catalog, complemented with, this is in the X-rays, complemented with O6 observations from Bregman et al. 2005 of 06-1032. We use Cloudy to follow the cooling of gas from 10 million degrees to 10,000 degrees. And in the process, we aggregate these gamma factors over here, which allow us to convert fluxes into mass cooling rates through the line. Comparing those rates against the rates obtained by fitting the X-ray continuum, we see that the iron 17 resonance line is quite absorbed. And from this decrement relative to the continuum, we are able to constrain the Mach number of the turbulent fields in the gas. Is it over? Okay. Thank you.
No. Hello, so poster number 4. My name is Bożena Czerny. This is about the broad line region in active galaxies. If you look at the line shape, you see that the line consists of 2 components, broad line and narrow line. And the explanation was the presence of the dust, which eats some photons and creates a gap between the regions. Now, some objects do not show this kind of a gap, and we pose the question, what is the problem? What is the reason? We thought that it's probably the broadband distribution of the incident radiation which causes the difference. But we did a lot of simulations with using Cloudy. This is a paper with Gary, and the answer was no. The difference in broadband spectrum is not responsible for this. On the other hand, the local density is responsible. So we need higher density in narrow line Seyfert 1 galaxies, which is puzzling. We don't have explanation for that. Perhaps it is the reason that this region is farther away in narrow line Seyfert 1 galaxies and the velocities are lower and we have more time to develop high density contrast, but that's only our guess. Anyway, the paper is now almost accepted for publication. And I have one more poster which, that one. It was without a number. That's a work in progress. When you look at the range of properties of quasars, you see that there is one formal parameter behind it. It was discovered during PCA analysis. The question is, what is this parameter? So from the beginning, many people claimed that this is the Eddington ratio. On the other hand, recently, it was shown that also the black hole mass changes systematically along this, which should not happen if the Eddington ratio is the right answer. We have the hypothesis that this quasar main sequence is actually similar to the stellar main sequence. In stars, the key parameter is the effective temperature. We postulate that in our case, this is the maximum temperature in the disk which causes this, or alternatively, you can say that this is the maximum in the broadband spectrum distribution. But that's a hypothesis, and we will try to prove that using cloudy, because in rare quasars we can see this, the presence or the location of this maximum. But that work is in progress, and in the frame of the past paper, I'm not sure if the hypothesis is correct. Maybe it's wrong. Thank you.
I didn't know that I was supposed to present my poster here, but so it was my surprise. But my idea with this work is that some years ago we did a model of NGC 7210, and as you know, that nebula has an abundance discrepancy problem in the sense that the abundances derived from recombination lines are larger than abundances derived from collisionally excited lines. When we constructed a model with cloudy, I noticed that the model also shows an abundance discrepancy. So I run models just extending or enhancing the abundance in order to make the abundance discrepancy disappear. And it did. You know, one can construct a theoretical nebula that don't have an abundance discrepancy problem. So we have to look at how people are doing observations, and my guess is that that abundance discrepancy is coming from the temperature gradient, which leads credence to the T-square theory that attributes that discrepancy to temperature gradients. Thank you.
Good morning, everyone. My name is Jose Espiritu, and in this poster, well, I work with my advisor, Antonio Peimbert, and we collaborate with Gloria Delgado. We present the results of observations of HH202, which is the brightest Herbig-Arrow object in the Orion Nebula. And the purpose of this work is to study the effect of the shock and the interstellar dust grains. So basically, we calculate the amount of dust that is being destroyed by the shock, and also we estimate the amount of oxygen and iron and nickel that is being incorporated into the gas by the means of dust destruction. Also, we study the abundance discrepancy along the shock, and we find that it is greater at the center of the shock, and we find that we can reconcile determinations from collision lines and recombination lines by producing thermal inhomogeneities in the form of the square parameter. And this is an interesting result because it had not been reported previously, especially in H2 regions. You can see it here. So yeah, if you want to know the details, please come check it out. It's poster number 6. Okay, thank you.
Good morning, I'm Sheila Flores. I'm working with Miriam Peña, and here we present high-resolution spectroscopy of a number of planetary nebulae and H2 regions, of the dwarf irregular galaxy NGC 3109, and compare their kinematic behavior with the one reported previously by Ott et al. Can be seen in this figure, the kinematic of the H1 gas. And we found that the planetary nebula and H2 regions follow really close this kinematic behavior of the gas. We also studied, present a revision of the chemical composition of the planetary nebula and H2 regions previously reported by Peña et al. 2007. But this time, instead of using Kingslow and Barlow ECFs, we used Delgado and Glada, and we didn't find really a big difference between the results for oxygen and neon. And we confirmed that the oxygen is enriched in this galaxy. Peña et al. Found it previously. And we also observed a little bit of neon enrichment predicted by stellar models by Caracas and Ventura. And if you want more details, you can come to the poster, please. Thank you.
Hi, we show here position velocity maps of the recombination lines and the collisionally excited lines with the objective to analyze the kinematics of those lines to help us to analyze and understand the abundance problem in the abundance discrepancy problem in those intensity lines.
Hi, good morning. My name is Veronica. I work with Dr. Morissette. And in this work, we try to model the infrared dust emission using cloudy models. We focus on two broad features at 11.5 and 30 microns that are observed in the infrared. We use the carbide silicon and magnesium sulfide molecules using spherical and ellipsoidal grains to try to reproduce the emission. And if you want more information, you can come to poster number 9. Thanks.
Buenos días. My name is Francisco Guzmán. I work as a postdoc in the University of Kentucky with Gary Ferland. And my poster is about the importance of the accuracy of atomic data in which astrophysical studies relay. In particular, the effect of L-changing collision and angular momentum changing, electron angular momentum changing by nearby passing ion. There are several theories which disagree in a factor of 6, and that reflects in the lines, and the recombination lines of hydrogen and helium, and that they differ in about 10% depending if you use one or the other theories. We have also looked into the two photons continuum, into the two photons continuum, and then there is also a difference, a change in the prediction of using one or the other theory. If you want to know more details, please contact me or visit my poster is number 10. Thank you very much.
Hi. I am going to, my poster is of chemical evolution models of Leo A. This is Leo A, is a dwarf irregular galaxy. It is a very low metallicity. It has a very low metallicity. And we did these chemical evolution models, but our observational constraints about the present time of the interstellar medium, we don't have an accurate number. No? So we have now spectrum and with his GTC, and but has a very faint lines, so we are going to use maybe cloudy in order to obtain this. Thank you.
Hello, I'm Al Kaplan. I'm a graduate student at the University of Texas at Austin, and I work with Dan Jaffe and Harriet Dinnerstein. And my poster is on using the row vibrational transitions of molecular hydrogen here to explore the excitation in physics in a variety of PDRs. Here are 3 examples on my poster. I have the Orion bar, the Horsehead Nebula, and planetary nebula M1-11. I've observed many more, but these are sort of the 3 nice representative examples. And by comparing to cloudy models, the molecular hydrogen treatment in cloudy, I can explore the types of excitation and microphysics within these PDRs using these molecular hydrogen lines. For these observations, I use this new instrument called IGRINS, which gets a large wavelength coverage, 1.5 to 2.5 microns at high resolution. So I can see many of these row vibrational molecular hydrogen transitions. So if you have any more questions, come by my poster. It's number 11. Thank you.
Hello, my name is Alexia Medina. I'm an undergraduate student working with Dr. Delgado Inglada. And here I present the poster number 12. It's about ICFs for sodium in planetary nebulae. Let me explain you very quickly. The chemical composition of planetary nebulae provide information about galaxies' evolution and nucleosynthesis in low-mass stars. As we cannot see all the ions present in the nebula, we need these factors called ionization correction factors. Here I present these factors for sodium in planetary nebula, which I've calculated using a grid of models computed with cloudy. So come to see the poster number 12 for more information. Thank you.
Buenos dias. My name is Mitchell Ravolsky. I just completed my 2nd year of graduate study at Georgia State University, so I'm looking forward to having more time to focus on my research now. Specifically, I'm trying to study mass outflow rates in nearby active galaxies. So I'm trying to understand how much material is being blown away from the supermassive black hole as a function of distance. So our process is to go along the slit. This is an image of Markarian 573. And measure all of the emission lines that we can see, and then calculate their ratios relative to H beta and correct them for reddening. Then I go through and calculate cloudy models at each and every position in order to understand the physical conditions such as the density and the column density and the covering factors in order to deduce the total amount of mass at each location. We combine that with the kinematics, and that gives us a mass outflow rate. So we find that in the outer regions, we can model the emission lines with very simple 1 to 2 component models. And closer to the nucleus, where we have lines covering a wide range of ionization, such as neutral oxygen and iron-10, we use multi-component models, and then we add fractions of those in order to get our final model. So the overall takeaway point is that I want to understand if the properties of the mass outflow, such as the peak amount of mass or the distance to which it can be driven, is fundamentally tied to a property of the AGN, such as the supermassive black hole mass or the Eddington ratio. If you have any questions, please come by my poster, number 13. Thank you.
Hi, my name is Jacqueline, and my project is about hydrodynamical models of 2 planetary nebulae, M132 and M315. And in this part, you can see the position velocity diagram. And the slits were placed in 3 different positions. And for M132, you can see 2 bright nodes and jet moving at high velocity. And for second planetary nebulae, M315, you can see a bright sphere and 2 nodes at high velocity too. And the model consists in a jet moving inside in the medium and AGV wind previously launched. And this part shows the result of our models. And they are in a good agreement with observations. And the most important thing of this project is that we, for both planetary nebulae, we use the same physical model and using different parameters. And thank you.
Everyone, my name is Jonathan. My poster is called the photogenization model of the ring nebula NGC 6088, associated to the Wolf-Rayet star WR 136. The model is based in a shell spectroscopy, and the basic ingredients of this model is to consider two gaseous components, one elliptical structure covered by one spherical low density one. And the idea is to try to reproduce these observations. The more interesting result is that to plot the different points of this model in a diagnostic diagram. Here is nitrogen versus oxygen tree lines, and this diagram usually employed to know if one region is mainly photogenized or this heat is originated by other sources. And we find that only considering a chemical homogeneous nebulae, nitrogen enhanced, we find points which in principle must not be there. Another of the result, the other results is that concerning the idea that we have chemical homogeneous nebulae, we found that the ICF to derive the nitrogen abundance in the nebula seems to be modified along this nebula, but this is just because the combination of two effects, the ionization structure and the relative contribution of each of these components. If you have another questions about these results, I will be at the poster number 16. Thank you.
Good morning. My name is Aitor Robleto. I am a master student from University of Guanajuato in Mexico. My supervisor is Dr. Torres Papaki. We are working in the problem of separating the contribution of the AGN from the contribution of star-forming regions to the in terms of ionization of gas in the case of Cipher-2 galaxies. For this, we want to develop a reliable method that can separate the contributions. We are using data cubes from the Khalifa survey, that is a survey of integral field spectroscopy. We are processing the data cubes with the software Starlight, so we can separate contribution from different simple stellar populations and contribution from a power law that we will expect from the AGN to the continuum, and determine some physical conditions from other lines in the spectra. We intend to input these parameters in different ionization models with cloudy and compare with the observational maps to see which of the different models explain better the observations. One first preliminary result is from this galaxy, and we have here a map of the contribution of the power law. We will expect in principle that this map the contribution of the AGN, but surprisingly we find that it represents better the different star-forming regions around the galaxy. We have to be extremely careful with interpretation of this map. We are currently working on it, but it appears that it could trace also the contribution of dusty star-forming regions in the galaxy. If you have questions, you can find me in poster number 17.
Good morning, everyone. I'm Francisco, and I present my poster about the kinematic of collisional excited lines and optical recombination lines. And we analyzed the spectrum of this nebula, and we are finding a ionization structure between the seals and the O's, and we're finding discrepancy between the kinematics of the oxygen 3 of the forbidden line and the oxygen 2 of the recombination lines. And we use the spectrums of high resolution, and we made the graphics between the ionization potential and the expansion velocity. And if you have questions and comments, my poster is number 18. Thank you.
Hi, good morning. My name is Mabel. I'm a PhD student here. I'm working with Antonio Peimbert. In this work, we study aged metal put to regions through standard observation techniques and through cloudy models. The primary goal is obtain abundances with a new ICF. We are going to use tailor-made models for H2 regions, and for this we are doing cloudy models using four stellar atmospheres, and use function, a loss photon function. For obtain an overall ionization structure, we use oxygen and oxygen plus plus, and for obtain an other ionization structure to other part, we use sulfur and sulfur plus plus. In this way, we can choose the best model by doing a comparison with observation data. If you have questions, my poster is 19. Thank you.
Yes, okay, I'll announce that. Let's thank all of our speakers regarding posters. We obviously have a very impressive array of posters, so we're all encouraged to go out and look at them carefully. Now, the conference photo is coming up, I think, next, and then, of course, coffee and snacks, and then we reassemble here. We'll begin at 11:30 sharp for the next talk in this session. Thank you. Sorry? Well done. Oh, yes, right.
Trying to convince
which output should be considered as pushed out of the system. This is the one I was thinking about.
Oh, okay. So sorry.
All I want to ask is,
Abraham, queremos ver si funciona esto.
That may have been the same trip she came to Austin. She spent a week. I was told I should have.
did put systems up there.
She was quite ill. Thank you very much.
Entra directo.
No, voy a cambiar al otro.
¿Lo hiciste de propósito para que salga hoy? No, es que en medio del blog y todas las cosas, toda la semana no puedo subir los miércoles. No, pero está bien, salió justo para el día de tu charla. No hubiera tenido que hacer ¿Tienes algún video o algo así? No. Es que de todas formas pensaba que hay que hacerlo en PDF. Déjame reviso. Ahora voy yo. ¿Te desconecto? HDMI? Sí, también tengo HDMI. ¿Voy a cerrar tu máquina, Graciela? Cierro tu máquina para que no se descargue. Sí, ok. Bloqueando la máquina primero. ¿Tienen HDMI ahora? Sí. Es que todavía ni siquiera estaba bien despierta. Muy bien, me desconecto. No se va a conectar bien. Déjalo cerrado. Sí, el de la cabeza no consigo. O sea, le pones acá RGB y allá es igual, ¿no? te puede regañar por esta decisión. ¿Te acuerdas de tu contraseña de correo? Ponla. Antes de que vayas. ¿Ya está el correo? Ya. Sí, pero es que como le dijiste de servidor UNAM, no, pero de servidor UNAM no, de aquí de astronomía. Porque el servidor UNAM también tienes cuenta y ya no se puede configurar ahí, no sé por qué, solo puedes acceder vía web. Me encantó, me encantó mucho. Sí, pues no, tuve que bajar otro adaptador. Saying that as solar roads email outline of any types of otherwise, I have to, I'm not talking to I think that the first one, the most important question is the Thank you very much. I was trying to do my best to shoot will rely on you in terms of one of the things I'll find out some outline of what Yes, do that first. Great. I much appreciate this. I'll be in a la Es que tío, gracias.
Ya no me interesa.
Sí.
Mientras tanto,
Sí, sí, claro.
Ah,
Sí,
ah,
no importa más entonces.
no, la verdad no.
Adiós.
So I hope it still works. Get your image up there on the screen.
And so nothing happens.
You should. Is this PowerPoint?
No, it's yes, it's okay. PowerPoint. No, but so you don't see it here.
That's because you haven't started. Well, that's true. Okay, just a moment.
Sí, no te preocupes, ahorita lo cambiamos, ahorita aparece, no worry.
Okay.
Please.
Just the notes.
Okay.
Okay.
¿Es tu apellido o nombre es
nombre es lo que los padres dan.
Sí.
Eso, entonces
Gracinia.
es Gracina.
Ok, Gracina.
Decimos nombre de pila. Cuando naces te llevan a bautizar en una pila. Te dan el nombre y por eso es nombre de pila. El nombre de pila es Gracina. Que no seas católico, no sé lo que sea. El primer nombre se le dice nombre de pila. Se le llama apellido.
Sorry.
El segundo es apellido.
Okay.
Creo que tengo una...
No voy. Gracias, doctor. Adelante, gracias.
Gracias. Me lo funciona así. Ok, el apuntador funciona como... ¿Qué es este B? 2 minutos. Ah. Porque como me dicen que él es muy... y yo seguro que voy a pasar de tiempo.
Welcome to the last two talks of this morning's session. As you can see on the screen, our next speaker will be Groznia Stasinska, and she will talk, as you see, about open problems in giant H2 regions. She thought about talking about giant problems in open H2 regions, but that's another talk, perhaps another conference. Please.
Thank you. So, how do I do it? It doesn't work. Okay. For decades, I have been constructing grids of models of giant H2 regions, first with MyCode and lately with Cloudy. And these H2 regions were very simple because I had many parameters to take into account, so the geometry was very simple. But of course, I know that giant H2 regions are very complicated objects. And so this is a list of topics I perhaps will have time to talk about. So let me start with strong line abundance determinations. As you know, giant H2 regions are the best test particles to determine the metallicities of galaxies, even to high redshift. And if we don't have direct information on the temperature of the emitting gas, then we use strong line methods to estimate the oxygen abundance. The idea is that we use some combinations of strong line intensities which are known to correlate with the oxygen abundance in objects for which we know the oxygen abundance. There are many problems with that. One is that different calibrations give very different values. You probably have all seen this diagram coming from Cooley and Ellison and showing the median of the mass metallicity relation in galaxies from the Sloan Digital Sky Survey, and you see that the differences are almost 1 dex. The other problem is that if the calibrations are based on observational samples, the results may be biased if you consider samples that are not identical to the calibrating sample. So here is an example. I'm showing H2 regions from the Sloan Digital Sky Survey for which you could determine the oxygen abundance with a direct method. And I made 2 categories. One, which I will call young, they are the blue ones. They have large equivalent widths of H beta. And the other ones, which I will call old, they are in red. They have low equivalent widths. And all these little panels are different indices to measure the abundance. And the red line is the line that is used to determine the abundance from a given line ratio. And you can see that in all cases, if you have young H2 regions, the strong line methods underestimate the true abundance. Yes, all the points are to the right of this curve. Here also. Here they are above, and then all of them, if you use the red line, underestimate the true abundance. And the opposite is true for the red objects. So you have a systematic bias just because you consider 2 samples which have different characteristics, and you cannot use such a simple way to determine the abundance. Now, if the calibrations are based on a model grid, the defining parameters of the grid must cover all the possibilities. And in general, this is not the case. So for example, I'm showing you the O2H determined using a grid where it is assumed that there is a formal relation between the N2O ratio and the O2H ratio. So this is it. And for the same objects, a method which doesn't assume anything on the N2O ratio. And you see that there are inconsistencies, just because in this method you imposed something which might not be true. So, in a nutshell, the principle of strong line methods is that you have 3 independent direct and light ratios based on these lines, and you have 4 main parameters determining the giant H2 regions, which are the effective temperature of the exciting stars, the famous ionization parameters, and these 2 abundance ratios. It happens that the effective temperature and the abundance happen to be correlated in giant H2 regions. The temperature, the average temperature, is correlated with the metallicity due to opacity effects in stellar atmospheres. And N2O is correlated to O2H because N is a secondary element. So giant H regions are considered as a 2-parameter family, metallicity and ionization parameter. What are the problems? One of the problems is that the ratio of, for example, O3 to H beta goes through a maximum as the oxygen abundance increases. At high oxygen abundances, the infrared lines are very important for the cooling, and so even if the oxygen abundance is high, the O3 optical line to H beta is low. So any abundances based on an indicator using this kind of ratio will be 2-valued. And if the abundance is in this region, then it is very ill-defined. The other thing is that the assumed correlations are not perfect, and secondary parameter modify the spectra of the giant H2 regions. And finally, the calibration. You have to ask whether the calibrating sample is well representative of the sample of objects that you want to analyze, or if you calibrate on model H2 regions, do your model H2 regions represent correctly reality? So I want to use a few slides to talk about a recent strong line method that we have implemented recently after years of, of work on that. And there are 2 main motivations. One is that the temperature and density structure are important in giant H2 regions models. So for example, this is a grid of models for instantaneous starburst of 2 megayears, assuming a spherical shell geometry. So the models have varying metallicities and ionization parameters. The metallicities are color-coded. And this is the same, but, sorry, I don't know. It's a spherical shell, so it's a hollow shell. And this is the same for 3 megayears. So you see that there is a big difference in the global shape of the model grid. Now, here I'm comparing a spherical shell with a filled shell, with a filled sphere model. And you also see that there is some difference in the global shape of the grid. And of course, depending on the grid that you will use, you will find a different abundance from strong lines. The other problem is the relation between O2H and N2O. So this is for a sample of giant H2 regions with very good observations. And these are the direct abundances, N2O versus O2H, with the associated errors. And this is for the same H2 regions, the N2O over O2H, using a strong line method, the one by Pilyugin. So you see that these plots are completely different. Now, so which one is closer to reality? For the moment, we don't know. Of course, the error bars in this plot are like orthogonal to the main trend. So part of the dispersion here may come from the error bars. But you see that there are some points which have very little error bars and which are outside the main trend. So this is something that we would like to take into account. So the method is to simultaneously derive the oxygen and nitrogen abundance in giant H2 regions. So it compares observed emission lines to a grid of photodissipation models without assuming any relation between O2H and N2O. The grid spans a wide range of O2H, N2O, ionization parameter, and covers different starburst stages and nebula geometries. Okay, so in contradiction with previous methods, we do not assume a strict relation between the hardness of the ionizing radiation field and the metallicity. And the other new thing is that we extract information on the nebula physics from what we call semi-strong emission lines. These lines are present in all the high-quality spectra that you have now. If you are not able to measure the temperature directly, these lines are available, except that people usually don't put them in the papers because they don't use it in their strong line methods, but they are in their spectra. So I will show you, okay, this ratio, argon-3 to neon-3, allows one to decide whether the H2 region is metal-rich or metal-poor. And if you use the helium-1 to H-beta, it allows you to infer the hardness of the radiation field. So let me show you that. Argon-3 and neon-3 have different dependencies on the electron temperature because they have different excitation thresholds. And on the other hand, argon to neon is expected to be roughly constant. Those are two primary elements. They are noble gases, so they are not suspected of dust depletion. So the argon-3 to neon-3 ratio is some kind of measure of the temperature. So if it is high, it means that the abundance will be low. It is, of course, not that simple because these ions, argon plus plus and neon plus plus, don't arise exactly from the same region, but you can use the observed O3 to O2 ratio to infer what is roughly the ionization. So this is our grid of models, argon-3 to neon-3 versus O3 to O2. In red, this is the high metallicity branch, and in blue, it's the low metallicity branch. So you see that you can very well separate both branches. The other thing is the effective temperature. So here I'm showing the famous O2 plus O3 to H-beta ratio as a function of O2H for different values of the hardness of the ionizing radiation field. So you can see that at high metallicity, if you observe this value, you will derive an abundance like this if the hardness is small, and an abundance like this if the hardness is high. So it is important to have an idea of the hardness in your region. And here I'm showing how helium-1 can work as a hardness indicator. So this is helium-1 to H-beta as a function of this. Again, colored by hardness. And you see that if for a given O2H, this gives you roughly an idea of the hardness. Actually, there are 2 points here that this region is not very well, I mean, those are not very well separated, so you cannot do better for the moment. I think that in the future you will be able to improve that using argon-4 to argon-3, but we need to have the data for argon-4. And in our grid, the distribution of stellar ages was rather sparse, so that makes these holes here. But this can be improved. So, okay, so here are the results. So here I'm showing again the previous temperature-based methods for the objects. And here is, for the same objects, the results of our method. There are less objects just because the values of neon 3 and argon 3 were not always published for these objects, which is, of course, because people didn't use it. So you see that, okay, it is dispersed similarly to this one. And the shape is different from that of the temperature-based method. You see roughly the points are towards higher metallicities. And this is due to the fact that very often models don't return the same value of the temperature that is measured. And just one thing about two simple strong line methods. We constructed a test sample of fake sources extracted from our grid of models. So here they are shown in green, the ionization parameter of the O2H, and this is the famous BPT diagram for H2 regions. And here is the result in N2O versus O2H using the Piliugin method, Piliugin strong line method, for these objects. And you see that this strong line method fallaciously strengthens a loose correlation. So this is important because very often people have the impression that, okay, the strong line method gave this, so the N2O and O2H are very well correlated, but it's a method which does this. Okay, so now, conclusion on bond. I am recalling the problems of the strong line methods, 1, 2, 3. And so bond solves 1 and 2 using the semi-strong lines, but it doesn't solve the calibration problem. The calibration problem is a different thing. The calibration problem, I mean, the models have to represent correctly the reality. Helium-2. I think I will drop it because I will not have too much time, but in one word, helium-2 lines are observed in many giant H2 regions, and okay, well, I will have to go very fast. And one of the explanations would be that they come from stars which are hotter than main sequence stars, mainly Wolf-Rayet stars, but there are many regions where you don't see the Wolf-Rayet signatures and which have helium-2. So, okay, so there are many possible solutions like shocks, X-rays, and binary stars, etc. Presence of massive stars, accounting for rotation population synthesis, which would enhance the effective temperatures, or photon leakage. For example, here I'm showing O3 to O2 versus O1 to O3, and O3 to O2 versus helium-2 to H beta for a sample of H2 regions. And these are models which are ionization bounded, and here are density bounded. So if you have density bounded models, okay, you of course get higher helium-2 to H beta, but that's not sufficient. I mean, you have to also explain the O1 to O3 or whatever. Structural properties of H2 regions. So you have to remember Will's talk this morning, who showed that the structure of H2 regions is far from a filled sphere or a shell. But as I told you before, the structure affects the emission line ratios. Now, what is the real structure of a giant H2 regions? There was an old paper by Kennicott who divided giant H2 regions in several broad groups. So there were high surface brightness H2 regions, those ones, diffuse H2 regions, shells, supergiant H2 regions, and multiple H2 region complexes. And okay, but actually, so if we build a grid of models, what kind of general distribution we have to use? And that's a very difficult problem. So the new generation of photonization model grids are still static photonization models, but they include physical assumptions about the nebula structures, like, for example, relating the radii of the H2 regions with the age of the ionizing clusters with the effect of winds, or then include the effect of winds and radiation pressure to determine the density structure. So there have been things like that. Now, another problem is the filamentary structure of giant H2 regions. You have seen all these kind of images. So it's observed, and it's also deduced from comparison between the mean electron density derived from the surface brightness of an H2 regions and the density derived from, for example, the S2 line ratio. And for example, in this case, we found that the filling factor was 0.005, very small. And it's common. It's common. Now, of course, the blobs don't float in the vacuum. Well, there is probably a diffuse medium around. But if you build a photonization model for this diffuse medium, you find that the blobs and the diffuse medium are not in pressure equilibrium. So I don't exactly know what this means. Probably Will have an answer to that. But that's bothering me. Okay. Leakage of photons. It's an important matter because ionizing photons may leak out of giant H2 regions and ionize the diffuse medium. So what does that mean?
Nothing.
They can ionize the intergalactic medium, and nowadays it's very popular to try to find out which photons reonize the universe after the Dark Ages. So, okay, for example, high surface brightness giant H2 regions, if they have the density distribution of this form, they all have leakage because if you write the equations, it's obvious many ionizing photons will leak out. But how are those representative of giant H2 regions? I have no idea. Now, people have said that objects with high O3 to O2 ratios may be leaking out because, okay, the O2 zone is not complete. But this argument is not correct because they forget about looking at what is O1. But on the other hand, you may have covering factors smaller than 1. And they have been, I call it 3D photonization modeling, models which take into account the complicated distribution of the blobs. So for example, there was a nice paper by Giamanco et al. Using cloudy. They considered small clumps, either optically thick or optically thin. And in that case, there is some leakage of photons. And they try to make the difference between optically thick and optically thin filaments. It was not very clear, but I mean, that was a first step to try to get perhaps a more realistic density distribution. Nowadays, there are pure 3D modelings of the ionization of fractal clouds. And there are even self-consistent dynamical simulations of turbulent molecular clouds, like those of Dale and al. And for example, they find that low mass clouds lead, actually low mass clouds and high mass clouds leak about the same amount of ionizing photons. So abundance discrepancy, I will be very short because you will hear of it a lot in other contexts, and you have already heard about it. So this is the abundance discrepancy factor. We know that it is real. This is, for example, an example of collisionally excited line measurements of O2H, and this is from recombination lines. So recombination lines give, in general, always give higher values. Possible solutions are temperature fluctuations, non-Maxwellian electron distributions, and abundance inhomogeneities. Maxwellian electron distributions, they have been convincingly ruled out by a recent paper by Ferland, Henney, Odell, and Peimbert. The problem with temperature fluctuation is not solved. You can produce temperature fluctuation by many mechanisms, but the problem is to obtain a value which is sufficient to explain the abundance discrepancy factors, and that is not solved. And the problem with abundance inhomogeneities, okay, you can say there are abundance inhomogeneities, but you have to find a physical scenario, and you have to check about the size of the clumps, the lifetimes, etc. So, okay, just one thing. In the case of the metal-rich droplets, it is the collisionally excited lines which better give the average metallicity, whereas in the case of temperature fluctuations, it is the recombination lines which give you a better idea of the metallicity. And my final slide is comparing the nebular abundance with those of young stars. This is a recent paper by Brezelin, Kudrytsky et al. So this gives metallicity of stars minus metallicity of gas for collisionally excited lines and for recombination lines, okay, as a function of metallicity. And so you see that at high metallicities, the recombination lines, those are closer to the stellar ones, but at low metallicity, this is not the case, and this is not understood. So conclusion, okay, you have heard of all this, and the challenge is to build grids of models by reducing the number of parameters which are important, but still giving them a physical importance. So it's not, and this is not solved yet. Each time I produce a grid, I'm not sure that it is the right grid to produce. Okay, thank you.
Notice that the symbol for helium-2 looks a lot like the word in English language hell. It obviously means is that if you wish to subtly insult someone, simply tell them to go to helium-2. They will know that you insult them. You will. Okay, questions?
I just wonder if the helium-2 problem might be connected to both materials.
Yes, it might be. He's asking whether the helium-2 problem is connected with oxygen-4 to oxygen-3.
Yes, I was struck. I was struck by the some of the outliers in your diagrams of N to O versus O to H, and I noticed that several of those with the very small error bars were in the sense of a nitrogen excess at a fixed oxygen abundance. I wonder if those could be attributed to H2 regions that have already been polluted by Wolf-Rayet stars and their winds that would naturally account for a nitrogen excess.
But all of them, in some sense, have been polluted in the past, because the nitrogen abundance is a result of the whole history. What you mean is the local yes. I don't think these are such cases, but it has been studied by some people like Manuel Peimbert and Cesar Esteban. There are cases where, but I think that those cases were always negative. I mean, they expect, for example, they studied objects with Wolf-Rayet stars, so you imagine that those expel the nitrogen, but finally the observed nitrogen abundance in those was not what they would expect. Am I correct? Mm.
Sorry, in general, if you use recombination lines and if you assume that the gas is well mixed, the nitrogen to oxygen ratio increases with the oxygen to hydrogen ratio. I don't know if this is what comes here.
While we wait for the next question, if perhaps the next speaker can come down and get set up, and we have time for another question for our current speaker. Don't know.
So it's just a comment on the leakage problem. I think the solution there needs to come from the observers, actually, because we can measure very well the number of ionizing photons in the gas, but what we don't know is the actual number of ionizing photons really that the stars are emitting to within the factor of 2 or so that you say the models predict. So in order to solve that, we really need the observers to tell us how many photons are actually being emitted in the first place.
Yes, there are a few cases now of blue compact galaxies where the leaking ionizing photons were observed in the spectra. And in all those cases, the leakage is about 8% or something. But this is for a specific class of galaxies, which are blue compact galaxies. Now, this wouldn't be sufficient, for example, to explain the reionization. Now, I have been to a conference on reionization, which was completely new for me, and there were many talks, and most of them didn't find anything. I mean, or not anything, or certainly not enough to reionize the universe. But you are right, it has to come from well, I mean, it's difficult to say, because if you want to have a global answer, I don't know how many objects you should be able to observe, because you can always observe a few and they will not be representative. But yes, you are right. Although I think that the fully dynamical models may give some insight, like, for example, the work of Dale, who made the simulation, hydro simulation, and found some global output, except that in those simulations they are not able to make many. So they made maybe 10 simulations and that's it.
Let's allow time for one more quick question.
Just a very quick comment. I'm afraid this is beginning to remind me of meteorology.
Okay, thank you very much. Okay, last speaker for the session is Antonio Peimbert. His title is Primordial Helium Abundance. Did the helium in your party balloon come from the Big Bang?
Okay, is this working? Yes. So I'm Antonio Peimbert. I will be talking about the primordial helium abundance. My main collaborators in this topic have been Manuel Peimbert and Valentina Luridiana, and I have a student that is starting to work on this, Mabel Valerdi. I chose this topic because I was finishing a paper when I had to choose a topic, and I sent it, and it was just approved, and as soon as it was approved, I popped it into the archive, and it showed up this morning, so it's perfect coincidence. So an outline. Why do we want to study the primordial helium abundance? How do we study the primordial helium abundance? Who is studying the primordial helium abundance? Are the first three topics. Also, I will say a little bit about the connection with Gary. Then I'll talk about our determination. I'll talk about uncertainty sources, which are very important in this subject. Then I will compare it with YP determinations by other groups. And at the end, I will talk a little bit about how we can get constraints on the number of neutrino families or on the neutron mean lifetime from this. Well, then, where to go from here? So why study the primordial helium abundance? Well, it's one of the Big Bang's three pillars. It's the expansion, the microwave background, and people nowadays forget that when the Big Bang theory was presented but not yet accepted, it predicted that there would be a primordial helium abundance, while the opposite theories assumed there would not be. So the fact that there is important, or was important, rather. Then, through studies of nucleosynthesis, we can understand the universe and universal constants. We can test whether the Big Bang is a standard Big Bang or it deviates in some way from it. Less cosmological, more locally. We can also study, well, the evolution of heavy element versus helium production, and that is related with the number of big stars and small stars being produced, et cetera, et cetera. If one is studying the chemical evolutions of galaxies, one needs a starting point, and that comes from YP. And studies like this also helps us to have a deeper understanding of H2 regions. What happens at extremely high temperatures in H2 regions? Is the helium temperature equal to the oxygen temperature? This is, of course, related to the T-square problem, and a few more things that we look into. Did I miss something? No. So understanding the universal constants, well, what I'm talking about here, historically one would look for the baryon to photon ratio by looking at YP, but nowadays the satellites do a much better job than us at doing that, so it's out of fashion. But we can still put constraints on things like the neutron mean lifetime and things like that. And especially, we can check whether the Big Bang is standard or not. There are a bunch of things that have been proposed that are non-standard Big Bang that would show up if the Big Bang was not standard, would show up as a delta YP, as a difference in YP between what is expected and what is found. So how can the primordial helium be determined? There are three main methods: satellites, as I said, WMAP and Planck, through the studies of the microwave background and isotropies. They can possibly find exquisitely fine, perfect values, and I'll talk about that a little bit later. You could also do it studying deuterium or lithium, but since all the primordial nucleosynthesis happens at the same time, they should be correlated with helium, with YP. And of course, our method is to study H2 regions and try to extrapolate from very low metallicity H2 regions to primordial abundances. So I'll say a little bit about the determinations from satellites. If you read their papers, if you believe in that, you find determinations with tiny error bars. So 13 parts in 100,000 is what they said in the last one. But if you keep on this for several years, this changes a little bit more than what they'd like. And more important than that, they are assuming that the Big Bang is a standard Big Bang. Even within the standard Big Bang scenario, they are assuming a lot of constants are perfectly well known. And I'll talk a little bit later about the neutrino mean lifetime how it's not as well defined as they say. Some sources claim that the error bars there are of about plus minus 1 second, but if you look at different papers in that area of physics, you'll find differences of about 8 or 9 seconds. Sorry, I said neutrino. Sorry, neutron. It started from you. Only the people who work with satellites use 5 digits in the YP determination. Most other people use 4 digits. I will use 4 digits, and I'll probably be saying many numbers in units of 1/10,000th of the total mass. Before I move, also if there is a 4th neutrino family, for instance, if the neutron is not, the mean lifetime of the neutron is not as well known, this would imply differences of about 1/1000th of the total mass of being helium. And if there's an extra neutrino family, that would mean about 1% more mass as in helium at the beginning of time. So those error bars at the beginning from satellites are just too optimistic. Well, from satellites you can do 2 things. That's the first one, and they do it and they're very happy, but they assume they know the mass, they knew the total mass, the baryonic mass, the expansion of the universe. They put all that into their simulations and they find these exquisite values, assuming they know everything else. Also, without assuming they know the neutron mean lifetime, the number of neutrinos, if they look at the acoustic oscillations, the 4th and 5th peaks are related to the number of electrons, of free electrons, at some point in the evolution of the Big Bang. And from those you can determine the primordial helium directly. This is a lot more solid. There are less things that go into this. However, the error bars are not as nice. So that's equivalent to 1 neutrino family, 0.2520 plus minus 0.014, which is a lot larger than what they'd like. If you can also do it, as I said, from deuterium or lithium. Lithium is not as good as deuterium. But these determinations, as with the satellites, are indirect, and they are not very restrictive. If I take the values from Cook et al. In a recent paper, the YP determination will have an error of 55/10,000ths in the end. It's a little bit high, the value that they find. So for these reasons, many people that do deuterium, they don't do the extra effort to calculate helium because it's just more effort and not very useful. And of course, there is the best way to do it, which is the way we do it. And so there are 3 groups that have been doing this for many years. I'm sure there are many more papers, but not by a group that has done several papers. So there's one group by Isotov. He's the first author in most papers, who has worked with Tuan, Stasinska, Guseva, and several others. Olive, Aber, and Skillman, and some others have done their own work. And then Peimbert, Luridiana, and a few others we have worked. And of course, I'll prove to you that this is the best determination, maybe. So a little bit about Isotov and company. They have been the observers of the set. Starting in 1994, they have observed over 100 objects. They have observed and studied over 100 objects. And in fact, all the objects by the Olive group were observed by Isotov, and most of our objects were also observed by Isotov. 80% of our objects, not 60% of our objects. Olive arrived into this a few years afterwards, and they were not happy with the work that Isotov was doing. They claimed that they were being they had made too many simplifications, and that they were not extracting as much information as they could from the data they had, and that the error bars they were presenting were too optimistic. So they took part of Isotov's data and they obtained their own YP value, and have done so for the past 2 decades. And then, well, there is our group. This group has passed for a couple of phases. The original one started in 1974. I cannot claim authorship for those papers, but these groups started it all. They present the first determination with this method, and they presented the method. But, well, now talking about me, I started working on this in the year 2000 with observations of NGC 346. And, well, we have done many more papers on that. Our approach is completely different. Instead of trying to find many objects, we find a few select objects, and we try to study them as well as we can. We do tailor-made models, cloudy models for each one of them. I'll talk a little bit later about the chemical evolution. So our information of chemical evolution, we take it from elsewhere, while the other two groups take it from within their own determinations. So our sample is these 5 objects. So if you know any one of them, you can feel part of this. If not, well, they are just 5 low metallicity extragalactic H2 regions. Well, before that, NGC 346 is the only one we observed. The other ones are data by Isotope et al. So I said I was going to talk a little bit about chemical evolution, delta Y over delta Z. Usually, in theory, we want to use all the heavy metals. In practice, we usually use only oxygen. It's a lot easier to get a handle on it. We take information from models of evolution, chemical evolution of small galaxies, as well as from comparing very low metallicity H2 regions with low and actually supersolar metallicity H2 regions. And we found this slope for this array. And once I've missed one, oh, never mind. Once we correct our determinations for this and for chemical evolution, we find our YP to be 2446 1/10,000 plus minus 29. And that plus minus 29 is very important, because if it was plus minus 100, it's not interesting at all. If it's plus minus 5, it becomes very restrictive. Plus minus 29 is intermediate, and we'd like to make it smaller. We have looked for the uncertainty sources in what we're doing. We have found 13 uncertainty sources. A few of those are statistical. A few of those are outside what we can do within H2 regions directly, so they become systematic. If we add them up, we have 18 units of error in the statistical part, 22 on the systematic part. Okay, so I'll take a small detour. What's the connection with Gary in these things we have? Our connection with Gary is in 2 ways. The atomic data for helium that we're using was derived by Gary and many of his collaborators. And, well, of course, we use Cloudy for a few parts of what we're doing. In particular, for the collisional excitation of the hydrogen lines, and for the ICF of helium. But the first one, and I don't see the other one. No, well, it's there. ICF. No, somewhere. It's there. I'll find it later. We are the only ones that use cloudy models. The other 2 groups don't really use them. But they have never made a model for each one of their objects, a careful model for each one of their objects. So the evolution of the atomic physics, well, it starts way before that, but this is what I know about. In the 1990s, Smith and Kingdon and Furland had some papers on it. Then, around the turn of the millennium, Benjamin and company had their own models. Then in 2005, Porter with Furland and other collaborators had a new determination. The difference between these 2 determinations was 40 units. And then in 2012 and 13, this same group, more or less, had newer data, and this changed again the determination by 27 units. And apparently they're working at it again. So apparently there's a paper that should be accepted soon that will change the helium atomic physics again. I don't know what will happen then. Sorry, that's like Guzman and Fairland and other people. So what do we use cloudy for? We want an ICF of helium plus. Many people assume that once you get very high ionization H2 regions, the ICF of helium will be 1. And it's nearly true. But there's a small difference of about 1%, or there can be about 1% difference. If you look at the green and the red curves that are there, the green curve represents neutron helium in the simulation. The red curve represents neutral hydrogen. And there's about a 1% or 2% difference in the total amount of neutral helium versus neutral hydrogen. This means that the ICF for this particular model is less than 1. So, well, that's something that we have to consider. We also have to consider photon leakage that will make it more complicated. Probably less important, but also more complicated to determine. We also look for the collisional excitation of the Balmer lines. Once you get to temperatures of 15,000 degrees or 20,000 degrees, that happens at very low metallicities, the very tail of the Maxwellian distribution can excite the Balmer lines. And that it's a few percent, but if we're looking for a few for determinations that are good to 1%, this becomes important. So this needs to be included. And it's different for each object. And there's a work that is kind of frozen in time about starlight excitation of neutral hydrogen and neutral helium lines. Our comparison with that of the other groups, well, goes like this. They use more objects than we do. AVER uses about 20 objects. Isotop and Company, they have used up to 100 objects, even if the last paper was only 45 objects. They determine this chemical evolution from within their own observations. We do it from outside data. They use the temperature that is used to determine the helium is different. AVER uses a temperature derived from helium-1 lines. Isotope use temperature derived from collisional lines, and there is a difference between those two things. AVER uses statistical corrections for fluorescent hydrogen lines. Isotope ignores the fluorescent effects of hydrogen lines. It's very small. The final result of AVER is very close to ours. It's 2449. Ours was 2446. But the error bar is larger, plus minus 40. While Isotope has a very different determination, 2551 plus minus 22. That's about 4 sigma away from what we're determining. So, well, as I was saying, the chemical abundance, what happens when you take it from within or from without? Our value was 3.3. AVER comes with 6.5 plus minus 3.5, which is consistent with us. Isotope finds something like 1 plus minus 1. So that means that I find that to be very small, that for each gram of oxygen that is produced, an additional gram of helium is produced. I expect more helium than oxygen to be produced. Well, I don't know. So going back, the error bars are important here. So this is the same table I just presented. So if you use more objects, you would expect the statistical errors to go down and nothing that could be done with the systematic effects. But if you're careless at doing this, the errors can go up instead of going down. If you ignore the collisional excitation of the hydrogen lines, you get a very large systematic. If the chemical evolution has error bars like the ones that AVER has, these can become very large. Isotope claims a very small error bar. I don't believe his error bar. I believe his error bar is closer to AVER's error bar, and I would put him also in this 30 value. I haven't spoken with him in many years. I don't know. So one has to be very careful about adding more objects into this. If we are comparing with satellites, as I said, if you assume standard Big Bang, there's no competition, they win. But let's turn it around. Let's compare our results with their results and check whether the Big Bang was a standard or not. Because that could be independent. Let's look at the number of neutrino families. It's been longly debated whether it's 3 or 4 or even 5 neutrino families, whether all these neutrino families were light at the time of the nucleosynthesis, or were already too heavy particles that were too heavy to be hyper-relativistic and blah, 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 blah. So what do we get? From our value, we get 2.89 plus minus 22, which is consistent with the number of 3.05, which is what physics calls 3 neutrino families. I don't know why they don't renormalize everything to 3, but it's 305 what we're looking at, or 405. So 2.89 is consistent with 3. 2.91 from Aver is also consistent with 3. And Isotov et al. Is 3.68 plus minus 16, which is not consistent neither with 3 nor with 4, but would be consistent with having a 4th neutrino family that partially decoupled during the time of nucleosynthesis. Sorry, before doing this, to do this, I have to assume I know the neutron mean lifetime. So I fix it to the canonical value, and I can do this. Or I can do the other thing around. I can fix the number of neutrino families at 3 and study the neutron mean lifetime. As I said, the physicists sometimes claim that the error there is about 1.1 second, 880 plus minus 1 second. But the 7 determinations they use to do this, the 7 best determinations they have, they're not really consistent with that. That band that is presented is actually 2 seconds, not 1.1 second. And in reality, most of those values are far away. Actually, the chi-squared value for that is 18.8 instead of something close to 6. So I wouldn't believe that. And these are the 7 best determinations. There are more determinations. Some of them are quite old, but this value has shifted quite a bit recently. Well, the past 2 decades. Apparently, this has something to do with the fact that there are 2 methods to determine the neutron lifetime, but I haven't dealt enough in this literature. But the fact is that there are 5 values that are low values that are more or less consistent with one another, and 2 values that are not consistent with the previous 5 values that are consistent with one another. And if we take those values, the best determination from each one of these 2 groups, they are very far apart. They are not consistent with each other. So if I take that, well, the physicists get organized with their neutron lifetime. We can compete a little bit there. And we obtain that the neutron main lifetime from our data is 870 seconds plus minus 14. Aver et al., 872 seconds plus minus 19. And Isotov et al., 921 seconds plus minus 11. So from this, I would say we prefer the lower value. This is us, and as well as the group of Aver. We're consistent with both high or low value, but we prefer the lower value. While Isotov would rather not talk about the neutron mean lifetime, they prefer a 4th neutrino family that was partially decoupled during Big Bang nucleosynthesis. Anyway, where do we go from here? We want more objects to be observed and modeled with a very good precision, not just adding them carelessly. We want improved atomic physics, so maybe there will be smaller error bars in the near future. And we want to study both the collisional excitation of the Balmer lines as well as starlight fluorescence of both hydrogen and helium lines. So thank you very much. And I'll leave you with my summary.
Thank you, Antonio. I seem to see a hand. Okay. I tell you what, I'm going to have you throw the tantrum second. I'm going to have Fran start out. Oh, okay. And then we'll get the tantrum just a moment.
Hi. I just want to say that some of the results of the submitted paper of Guzman et al. 2016 are presented in poster 10. Second is, Are you not afraid that only 6 objects will be a non-representative sample?
Well, you should be able to obtain the primordial helium from any one object. Because this object, well, if you understand the object, the material comes from the Big Bang. It has been evolved through a few generations of stars. We try to look for low metallicity objects, so not too many generations of stars. And, well, it should be, you should be able to do it from any one object. Of course, if the error bars are too large, there's a problem. So 5 objects are better than 1, so still can be done. 100 objects are better than 5, so in principle it can be done, but one has to be careful for each object one adds to something.
We have a tantrum coming, but that would be a great way to end this session, I think, with a tantrum. So before we do that, let's see, yes.
Thank you for the presentation. I just wanted to ask, in this new paper you are publishing today, how do you deal with the underlying stellar population for these objects?
Well,
do you have information from other sources, or?
Well, we have some studies of underlying absorption, and in both helium and hydrogen lines, we have done some statistical analysis. We have looked at many synthetic spectra and tried to correct for that. That's one part of the equation. The other part is we also look for objects with very high equivalence widths to